Okay, let's continue our discussion. So here we have example 8.2. A copper wire of length 2.2 meter and a steel wire of length 1.6 meter, both of diameter 3.0 millimeter, are connected into it. So here we have copper wire of length 2.2 meter and a steel wire of length 1.6 meter. These two are connected into it at this point, and diameter of these two wires is the same, 3.0 millimeter. Now, when stressed by a load, the net elongation is found to be 0.70 millimeter. So let's put this load here. So there will be elongation. I'm not especially drawing that elongation, but let me mark here. So there will be elongation in these two wires, and the net elongation is given. That is elongation in copper wire, let's say delta LC, and elongation in steel wire is given here 0.70. Mind it, here we have two significant figures. This 0 is also significant here. So this much millimeter. Or you can write 7.0 into 10 to the power minus 4 meter. So combined elongation we have obtained this plus this. Now we have to obtain this load. So one thing, if we are considering that the weight of these two wires is much lower compared to this weight, so we can think of that the tension produced by this weight will be the same across the wire, means the same across this system of these two wires. So we can say that the tensile stress in these two wires will be the same. So no matter we are talking about the tensile stress in the copper wire or in steel wire, these two should be the same. And then we can write this tensile stress is nothing but Young's modulus of copper wire into strain in copper wire equals to Young's modulus in steel wire into strain in steel wire. Then we can say this Young's modulus we can find out from the table. So let me write it here. YC for copper wire, Young's modulus should be this one here, 110 into 10 to the power 9 Newton per square meter. So 110, I can write it up to two significant figure, 1.1 into 10 to the power. Here it was 9, so we have to write now 11 Newton per square meter. And then for this steel, where is this? Okay, here 200 into 10 to the power 9 Newton per square meter. So we can write 200, instead of 200 I'm writing 2.0 into 10 to the power 9. Instead of that I'm writing here 10 to the power 11 Newton per square meter. Okay, I have kept here up to two significant figures because look here, every measurement is given up to two significant figures. So I would like to keep the answer also up to that. So this one will be now, and this, this strain will be the change in length of this copper wire divided by length of this copper wire, and here we can write once again YC, and then here YS, the change in length in this, and divided by LS. Now what are the lengths? So LC and LS, let me write it here. This is copper wire is 2.2 meter and steel wire is 1.6 meter. So this is 2.2 meter and this is 1.6 meter. So I can write, let me rearrange these terms. Delta LC divided by delta LS, this should be delta LC divided by delta LS, this should be Young's modulus for steel into LC divided by Young's modulus for copper and into LS. So the only thing we are going to do now, we have all the things here and we have to solve for this, and you do it by yourself. It should come 2.5, or we can write delta LC is 2.5 times of delta LS, means in copper there is 2.5 times elongation compared to this steel. So you can find out which one is more stiff. Okay, so here delta LC plus delta LS is 7.0 into 10 to the power minus 4 meter, and delta LC is 2.5 times of delta LS. So we can write 2.5 times delta LS instead of LC, and plus delta LS equals to, from here Not to be confused, I am just replacing this thing with 2.5 into delta LS here. So this will be 7.0 into 10 to the power. This is 7.0 into 10 to the power minus 4 meter. Okay, now you can see this is 2.5 plus this one 3.5. You should calculate this thing by yourself. 7.0 into 10 to the power minus 4 meter, and let me write it directly. Delta LS will be 2.0 into 10 to the power minus 4 meter, and then you can find out what is the delta LC. So delta LC will be 2.5 times of this value, so it will be 5.0 into 10 to the power minus 4 meter. So here we have elongation in the copper wire and in the steel wire separately. Now we can apply any of these two things to get what is the load applied here. So we can write stress in steel wire should be equal to Young's modulus steel wire into strain in the steel wire, and the stress is nothing but load given to the steel wire divided by cross sectional area, and this is ys, and this will be delta ls, this is s divided by ls, and cross sectional area. So from here we can find out weight. Let me do little more here. So this will be ys into delta ls into area, cross sectional area, divided by ls. This one we have delta ys is given here 2.0 into 10 to the power 11 newton per square meter. 2.0 into 10 to the power 11 newton per square meter, and then delta ls we have just obtained somewhere here. So it will be 2.0 into 10 to the power minus 4 meter, and then area will be pi r square, and radius will be 1.5 millimeter. So we can write here pi into r square. R square will be 1.5 millimeter, or you can write 1.5 into 10 to the power minus 3 meter, and square of this thing will be the area divided by length of this steel wire. And what is the length? Length is 1.6 meter. So 1.6 meter. Now you have to solve it for the weight here, and this will be in Newton. So try it by yourself, and ultimately you will get here 17.66 into 10 Newton. And let me keep it up to only two significant figures. So it will be 1.8 nearly into 10 to the power 2 Newton. So this is the weight. So this is all for this video.